Okay, we've started talking about force types, and so remember that the only force types that we're going to have in this class um, are field forces, which to us is just gravity. I could just write gravity here, but it's actually part of a slightly broader group that in later classes might include electric fields, magnetic fields. So I'm just going to call these field forces. But for us, uh, that's a simple thing. Field forces just mean the force of gravity, the weight. Um, and so that's just a downward force of the mass of the object times 9.81. Besides that, the only forces that you ever have to deal with are contact forces. And contact forces are broken up into three categories. The first one is pushing contact. The second one is pulling contact, which we're going to think of as applied by cables, strings, ropes, those kind of things. And then the last type is friction. Um, and so what this means, excuse me, if you're looking at a problem and there's all sorts of things going on, the object that you're looking at, this box or this card or something, has a million things happening to it. It's easy to break it down and just be clear to yourself about what kind of forces are acting. Um, there is a weight force, and so you apply that. Uh, and then you just go around the boundary of the object looking for places where other things are making contact with the boundary. You go around, you see a place where the two things are pushing against each other, you apply a pushing force, the rules of a pushing force. You keep going around, you find a place where they're pulling on each other, then it's the rules of a pulling force. And so by just being disciplined with yourself about the types of forces you're dealing with, the rules for each type of force, you can take what seems like a very complicated thing and make it sort of simple. Okay, so we're talking about the contact forces now. So this is us. Okay, we've already talked about how to deal with the weight. That's easy. That's just 9.81 meters per second squared times the mass of the object. Now we're dealing with the contact forces. And so for the contact forces, the first type is a pushing contact force. So what does it mean for two objects to be pushing on each other? Well, you're always, when you're dealing with forces, going to first choose an object that you're going to isolate, that you're going to be analyzing. And a pushing force is a force that prevents the chosen object from crossing the boundary into the contacting object. Okay, so what would happen if there were no pushing forces? Well, for example, when you're standing up, the floor is pushing on you. If that pushing force that the floor applies up to you suddenly disappeared, you would sink into the floor. You would cross the boundary into the floor. You could think of the floor turning into air, water, or something, and you would sink right in. It's that pushing force that keeps you from crossing the boundary into that contacting object. So pushing forces are, give me my space forces. Okay, so for example, let's think about a case where we have two carts touching each other. We'll give them each a mass. So let's say that the one on the left has a mass of 1 kilogram, the one on the right has a mass of 2 kilograms, and let's say that there are forces applied this way on the left one and to the left on the right one. I just made up those numbers, but okay, so where do we see these pushing forces? Well, if we think of the 1 kilogram cart, and I'll draw the boundary of that cart the way we do free body diagrams. We see pushing contact forces on our chosen object here because the ground is keeping the cart from sinking into it. And here because the object on the right is keeping our cart from crossing the boundary into it. Okay, give me my space. They're separating from each other. And what about the other one? So the 2 kilogram cart on the right go around the boundary and down at the ground, there's contact with our chosen object from the ground that keeps our chosen object from sinking into the ground. That means that's a pushing force. And then keep going around the boundary and you get to the left side and there's contact over there. That's a pushing force. Okay, so each of these has two forces pushing on it. In order to put these into a free body diagram, you have to know the directions of these pushing forces. So what do we know about the directions of pushing forces? Well, there's a rule for this. It's a very clear rule. It's kind of a mouthful to say, but you just have to remember the rule for this. You just have to put it in your head and stick it there and keep it there, okay? So the push force direction is perpendicular to the surface of contact and toward the chosen object. So every time you see two objects pushing on each other, once you've chosen your object to isolate, this is the rule for that force direction. It always follows these rules. Usually you won't know the magnitude of these forces. You'll have to calculate those. And so you'll need a variable to represent these. So what are some common names for the variables? So remember variables, you can give it any name you want, X, Y, P, whatever. It's just a variable name. But in order to communicate with other people who are trying to understand the physics you're doing, there are some common ones. So common variable names for pushing forces. One is capital N. That stands for normal. So a lot of times these pushing forces are called normal forces. And why is it given that name? Because normal is another word for perpendicular. And so since these forces are perpendicular to the surface, it sort of makes sense in some way. This normal means perpendicular. And the second one that you see a lot is a capital R. That stands for reaction force. Okay, so let's go back up to this example that I did, and let's actually draw the free body diagrams of those two carts following these rules. Okay, so a free body diagram of the 1 kilogram cart. Okay, so what do we know? What do we know about this? First of all, everything has a weight force attached to it, unless you're in outer space. So, and not even outer space. You can't even be on a space station. You need to be far outer space, away from the influence of planets and stuff. Everything you deal with is going to have a weight. Okay, so this has a mass of 1 kilogram. And so there's a downward force of 1 kilogram times 9.81 meters per second squared, or in other words, for this, 9.81 newtons. Now that we're done with the field forces, the weight, now we can just go around the boundary and look for places where our chosen object makes contact with the surroundings. There's contact between the wheels and the ground. We can treat this as happening at one place because we're still treating these as particles that don't have any length, so everything happens at one place. Okay, well, that's a pushing force because the ground is keeping the object from sinking into it. So now we just follow the rules of the direction of a pushing force. Here's the surface of contact. So our pushing force is perpendicular to that, toward the chosen object. Okay, that's the direction of the pushing force. And I'm going to call this the normal force. And since this is body 1, I'm going to call this N1. Now we're done with the force that's applied by the ground. Now keep going around the boundary, and you also have contact with the surroundings on the right side. That's also a pushing force. This force is a give me my space force. It's keeping our chosen object from entering the boundary of the contacting object. So this force direction is perpendicular to the surface of contact, toward the chosen object, and I'll call this one R1. And that's it. If you keep going around the boundary, there's no contact with other things, so you're done. That's a complete free body diagram for the 1 kilogram cart. Let's do a free body diagram for the 2 kilogram cart. So there's an outline of the boundary. There's a weight force that's equal to 2 kilograms times 9.81. So this is 19.62 newtons. Now we're done with the weight force. So all we need are the contact forces. Again, the ground is pushing this away. And here's the surface of contact. So the pushing force from the ground is perpendicular to that surface of contact toward the chosen body. I'll call this N2. we're done with that force from the ground. So now keep going around the boundary. You get to the left side, and there's a pushing force applied by the cart on the left. It's perpendicular to this surface of contact toward our chosen body. So that's R2. And okay, I'm getting so focused on the contact forces here, these pushing forces. I don't want to forget about those external forces that are applied in the problem, that 50 Newton force that's applied to the 1 kilogram and the 100 Newton force that's applied to the 2. So those have to go in here also. There's the 50 Newton there and the 100 Newton there. And you might say, like, well, aren't those pushing forces too? Well, yeah, they look like pushing forces, but we don't even really have to think about what kind of forces those are, because everything about them is just given. I'm just going to call them external forces. We don't know if that's a bird applying that or a strong wind or whatever. It's just given to us, so we just put it in there. But be sure you put them on the body to which they're applied. Notice that 50 Newton force doesn't show up on cart 2, and that 100 Newton force doesn't show up on cart 1. If two objects are pushing on each other, so if these two objects are pushing on each other, and you switch from one of the objects being your chosen objects to the other. You switch from one of these two objects, the objects, being your chosen object, to the other. Okay, so this is a very specific set of rules for when this applies. Then the force magnitudes of that pushing force are the same. In other words, you're going to use the same variable for both of them. This is actually required by a law called Newton's third law. We'll talk about that more a little bit later. But for now, just for using it correctly, all you have to think about is this stuff that I've said here. And so I'm going to redo these free body diagrams one more time using this requirement. Okay, so my free body diagram for the 1 kilogram cart. We have the weight force. We have the pushing force from the ground. We have the pushing force from the 2 kilogram cart that's this way. I could call it R1 again. I'm going to just call it R. And now I'm going to go to the free body diagram of the second cart, the 2 kilogram cart, and you'll see how this Newton's third law rule applies. Okay, so We have the downward force of gravity, 19.62. We have a pushing force from the ground, N2. And then when we get to the pushing force on the 2 kilogram cart from the 1 kilogram cart, it's still this direction. But notice that this is a contact between these two bodies, and we're just isolating the other body. Okay, so this is a case where we know the magnitude has to be the same as that magnitude we saw on the other one. And so this force has to be R. These two have to be the same. Why aren't N1 and N2 the same? Because it's not a case where we have two objects pushing against each other and we're just switching the body that we're isolating. In this case, so let's look at the free body diagram for body 1. We have a pushing force between the cart and the ground. Okay. In order to have the magnitude of these forces be the same, we'd have to go from isolating the cart to isolating the ground, because those are the two things that are applying forces to each other. We didn't do that. We didn't isolate the ground. And so this is not a case where those force magnitudes have to be the same. And if I was a really forgetful type person, which obviously I'm not, I would have had to go back and, I would have maybe forgotten to put in these external forces again because I was so concentrating on the pushing forces. And then I'd have to go back and do another video and embed it in here unnaturally. That's crazy. So anyways, remember that you have that 50 Newton force on this side and that 100 Newton force on this side. Those externally applied forces always have to go in there. And that's all I have to say about that. And pulling forces, they don't have to happen through a cable, but a pulling force could always be replaced by a cable contact. And that's really, I think, a nice way to think about it. Think about a contact force between two objects. What would happen if you replaced that with a string, like an infinitely strong string? Would the force still be able to act, or would it just scrunch the string up and the force would disappear? So think of this as a case where the contact could be replaced by a cable. And a cable, I just mean a string or a rope. So an example of a pulling force. So let's say that we have two carts. And they're joined by some kind of coupling thing like train cars. Let's say that the one on the left has a mass of 20 kilograms and the one on the right has a mass of 30 kilograms. And let's say there's a force applied externally of 500 newtons that's pulling the whole system to the right. Well, notice that if you think about this, this could be made out of steel with a pin connecting them. But in this particular application, you could replace that coupling system with a strong string, and all the same stuff would happen. The 500 Newton force would pull the 30 kilogram cart to the right, and that would pull the 20 kilogram cart to the right. So this is a pulling force. So let's think about what's going on with each of these. So the 20 kilogram cart, if we think about the contact forces, is there a pulling force between the ground and the cart? You know, on the cart applied by the ground? No, that is a pushing force. Okay, so that is still, that's still a give me my space kind of force. That's a force that's keeping the cart from sinking through the boundary of the ground. But over here, the contact between the 20 and the 30 could be replaced by a string. And so this is a pulling force. So this is the type of force that we're talking about now. What about the 30 kilogram cart? What's going on with that one? Well, again, there's a pushing force that's keeping the cart from sinking into the ground. And again, the force that's applied on this side could be replaced by a string, you know, or the contact could be replaced by a string contact. So this is a pulling force. And so these two red forces are the things that we're talking about now. So again, just like with pushing forces, there are rules for the direction of a pulling force. So if you have a pulling force, the rule is, imagine that you replace that contact with a string. So replace that contact with a string. I'll call it a cable. Then the force is along the line of the cable. And this time it's away from the chosen body. Remember, the pushing force was towards. This pulling force is away from the chosen object. Okay, well, let's try applying that to this picture that I've drawn up here, these two carts that are connected by a coupler. So let's start with a free body diagram of the 20 kilogram cart. You have a weight force that's equal to 20 kilograms times 9.81 meters per second squared. That gives you 196.2 newtons down. You have a pushing force from the ground that I'm going to call N20. And by the way, this can be confusing. I'm going to be using these capital N's as variables and also capital N's to represent newtons for units. When I'm using a capital N as a variable name, I'm always going to give it the fancy hat and shoes. And then the plain capital N is going to always represent newtons. So that's how you can tell that this is not newtons. This is a normal force. This is newtons. Okay, so that's all the stuff we talked about before this. Now what about the pulling force on the left? That's along the line of the cable, away from the body. And I'm going to call that T1. I'll get that written down in a second. The common variable name for pulling forces that we're going to use is a T for tension, like the tension in a cable. Now a free body diagram for the 30 kilogram cart. Here's the outline. The weight force is 30 times 9.81, so that's 294.3 newtons. There's a pushing force from the ground. I'm going to call that variable N30. Keep going around the boundary, and the only other place where there's a contact force is the pulling force. Let me be a little careful with that, because we do have that 500 Newton force, remember. So that 500 Newton force is applied over here. But the only other contact force is this, and I'm going to call that T2. And again, that follows the rules of a pulling force. Common variable names. For pulling force, we're going to use T, and that is short for tension, like the tension in a string or a cable. Okay, what about the Newton's third law type stuff that we talked about with pushing forces? So notice that any two objects that are connected by the same cable it has to be the same cable. Even if that cable is imaginary, okay, even if we've replaced a different kind of contact with that cable, if they're connected by that same cable, even a cable that passes through pulleys, and we'll do some problems with pulleys later. The magnitude of the pull force, the pull forces on the two bodies are the same. So let me do this one more time. So the free body diagram of the 20. We have the 196.2 there. We have the N20 there. And I'm going to call this force T. And now we'll go to the free body diagram of the 30 kilogram cart. We have the weight force of 294.3. We have the pushing force that I'll call N30. We have that externally applied 500 newtons. And then here we have a pulling force. These two are connected by that same imaginary cable. That cable is holding these two things together. And so these have the same magnitude. And so I'm going to use the same variable name. Okay, So those are the rules for a free body diagram. Now we've done pushing forces and pulling forces. Let me do an example problem that incorporates some of this stuff. So let's say that we have a track, and one side of it is at an angle. For now, you don't need to know what that angle is. To actually do the calculations, you would have to know if that's 20 degrees or whatever. And let's say that there's a pulley at the corner. And let's say that on this side, there's a cart with a mass of 10 kilograms. And there's a cable that goes from the cart over the pulley and connects to a mass on the other side of 5 kilograms that's hanging. Okay. And let's also say that there's a 5 Newton force pulling on the 10 kilogram cart that way. And we want to draw free body diagrams of the two objects. Well, I'll start with a free body diagram of the 10 kilogram cart. I'm going to draw it at the same angle that it really exists at. So there's the outline of the object. There's a weight force straight down that's equal to 10 times 9.81. So 98.1 newtons down. And now I'm going to go around the boundary and look for forces that are applied to the boundary, contact forces, and I'm also going to include this 5 Newton force that acts on the 10. There's a pushing force at this wheel, and I'm just drawing this dotted line to emphasize that, remember that the rule says that this pushing force has to be perpendicular to that surface. So it's going to be at an angle. It's not going to be straight up. Okay? That pushing force isn't going to be parallel to that weight force. And I'll call that N10. If you keep going around counterclockwise from there, you get to the cable force. That force is going to be along the line of the cable, away from the chosen body. I'll name that T. And then keep going around and you get to that externally applied force. We don't have to know what's applying that. That's given in the problem. And so that has a magnitude of 5 newtons. And so now, once you complete your loop around the boundary, and there's no more places where there's contact, then you know you're done with your free body diagram. We've dealt with the weight force, every contact force. We dealt with each contact force individually according to the rules of that type of force, and so we know we're done. Okay, what about the 5 kilogram? All right, well, that's a mass like this. There is a weight that's equal to 5 times 9.81. So that's 49.05 newtons down. And now we go around the boundary of this object looking for contact. There's contact with that cable at the top. Since it's a cable, it's a pulling force, and so the rules say along the line of the cable, away from the chosen body. And since that's the cable, and the only thing it touches is pulleys in between, it has to have the same magnitude of force as that pulling force on the 10. So this has the same name T as the first one. Okay. Now what we're going to see is that you can use these variable names and these directions in Newton's second law to calculate accelerations and forces and stuff. That's going to be the next step after we're done talking about free body diagrams. But this gives you everything you need to know about drawing free body diagrams, knowing the directions of forces for contact forces due to pushing and contact forces due to pulling.